finish this section off with a little more numeration. We've pretty much done everything that we needed to do, but there's a little bit more, kind of some of the bigger problems or kind of trickier problems that we might want to look at a couple examples of here. So that's what we're going to do in this last lecture for this section. I am back in the barn. It is very cold this morning, so I do have my hot drink to keep me warm. Okay. So remember that we were looking at numbers in different bases. And what we did last time was go from a certain base, let's say like base 4, and we changed it to our regular base 10. Then we would take a number that was in base 10 and change it to base 2. But let's say, as a bigger, trickier problem, just means more practice, let's say that we were given this. Change, let's see, 46T1 in base 11 to base 3. Not quite sure. Actually, you know what? We've used base 3 before. Let's use base 5. Let's just mix it up a little bit, make it a little bit different. We can do whatever we want. Okay, so we talked about base 11 being weird because since there are 10 digits, since there are 11 digits, the 10 gets represented as a T for 10 because the 0 represents 0. So base 11, weird. Base 5, weird. Don't know why you'd ever want to use them, except that it helps us practice a little bit. So in order to go from base 11 to base 5, what we need to do is go through the original base 10. We need to get it back to our original. So we're going to start with the 46T1. And then remember, this is in base 11. And we're going to expand this out like we did before. Now remember, because this is in base 11, this means that this is 11 to the 0. This one is 11 to the 1. This one is 11 to the 2. And this one is 11 to the, that is not an 11, 11 to the 3. Now, I don't really know what 11 to the 3rd power is, and so we will crack out our calculator here. 11 to the 3rd power is 1,331. So over here to the side, we'll say 11 to the 3rd is 1,331, and 11 squared, hopefully we remember that that's 121. So that's just to help us go through his. Now remember, as we're going to do this, we're going to multiply down here. So we're going to multiply the 4 times the 11 to the 3rd. And again, I don't know what that is. So we'll take our 11 to the 3rd, 1,331 times 4, gives us 5,324, plus, then we're going to take the 6 and multiply it by 11 squared. So 6 times 121 gives us 726. Now, luckily, the rest I don't need my calculator for. So remember that this is 10. So this is 10 times 11 would be 110. And remember, 11 to the 0 is just 1, so this last one will just be a 1. So we multiply, expand out each part of the number, and then we add them all together. So 5,324 plus 726 plus 110 plus 1. Ooh, this is interesting. It ends up giving us 6,161, and this is in base 10. I always find it funny when I just make these things up, but how funny the numbers come out and they end up with some weird pattern that we never would have expected, but there we go, we've got a pattern. Now, it would be nice if we could just leave it as 6,161, but for whatever reason, these people want us to go to base 5. Yay, thank you very much. So we're only halfway there. Now we've got to think about going to the base 5 part of it. Now over here to the side again, I'm going to write some numbers, some base 5 or some powers of 5. So 5 to the 0 is 1, 5 to the 1 is 5, 5 squared is 25. 5 cubed is 125. 5 to the 4th is 625. Let's see what 5 to the 5th is 3,125, and 5 to the 6th is 15,625. Okay, so again, these first couple you know, but we need to go further, so we make a nice little list of them. Now remember that the way this works is we're going to think about this as like dividing into. So this number is too big, isn't it? This number goes in to 6,131. So we can 61. We can divide 6,161 by 3125. And it goes in there just one time, right? So there's 1 of the 5 to the 5ths. Now remember, what we need here is the remainder. The remainder is the important part. So if we take 6,161 and we subtract a 3125, then we're left with 3,036. And our remainder is what we bring down here. So 3,036. Now, 625 definitely goes into that, doesn't it? But I don't really know how many times, so I'm going to use my calculator to help us. So if I say 36 and divide it by 625, I get 4.85, but I only really want the whole number here. So there are 4 of the 625s. Now, 4 times 625 is 2,500. So this part equals 2,500. So what's left over that would get us up to the 3036? So 3036 minus 2,500 would give us 536 as a remainder. So if we divide by 625, we get 4 with a remainder of 536. So then we bring 536 to the side here. Now we're at the next number in line. Are there some 125s in 536? There most certainly are. I don't know how many, so I'm going to divide again. 536 divided by 125 gives me 4 of those, and then some remainder. So there are 4 125s. So 4 times 125 is 500. Okay, so that little bit equals 500, which means the remainder here is 36, right? If that's 500, there's 36 left over. Okay, then we write the remainder here. 36 equals, hold on one second. Just checking on the camera. So 36 equals, and then we look at the next number in line. Now there is 125 in 36. But what's the remainder? If we take away 25, we're still left with 11. Now 11 comes down here, and we're on the next number in line. So how many 5s are there in 11? There are 2 5s, which makes 10, which means the remainder is going to be 1. So the remainder is 1, which means our last step is just 1 times 5 to the 0. Okay, so remember, it's a division and then you see what's left over. So division and you're looking for the remainder. Now remember, we need to have all of these numbers, 5, 4, 3, 2, 1, 0. Do not skip any of them. And once we've got them, remember that the answer there is vertical. So 1, 4, 4, 1, 2, 1, and this is in base 5. So this original number, 46T1 in base 11, was equal to 6,161 in base 10, which is equal to 1, 4, 4, 1, 2, 1 in base 5. So that's kind of the big problem, is doing both, going from one weird base to another weird base. So let me take a sip here. So also from last time, remember that we have binary, and binary is probably after our base 10, binary is the go-to base, because as we said, everything that uses computers, microchips, anything like that, uses binary. But binary was just a fancy way to say base 2. Base 2. So, in base 2, remember that there are only 2 digits. The only 2 digits that we have are 0 or 1. 0 or 1. So let's just do a little bit of a review there. Let's say they gave us 1, 1, 0, 0, 1, 1 in binary or base 2. And they want us to change this into regular base 10. Okay, regular base 10. So now remember, again, this is going to be 2 to the 0. This one is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and 2 to the 5. Now, there either is 1 or there isn't 1. That's our 2 options, and that's why binary is nice. It either is or isn't. So in this case, there is 1, 2 to the 5th. Now, 2 to the 5th, if you remember from last time or calculate it out right now, is 32. So there is a 32. There is also a 2 to the 4th, which is a 16. But is there any 2 to the 3rd? No. A 2 squared? No. A 2 to the 1st? Yes. And 2 to the 1st is just 2. And is there a 2 to the 0? Yes. And that's just 1. So all together, if we add those guys together, we get 32 plus 16 plus 2 plus 1, which is the number 51. And that's in base 10. So this 110011 is the representation of the number 51. So one other thing though is that because binary or base 2 gets used so often and your computer and your calculator is doing it, the idea of switching back and forth from base 2 to base 10 to base 2 to base 10 to do calculations becomes a bit of a pain in the neck. So what we want to do is a little addition problem here. And certainly in order to do computer science, you have to get far more intricate than division or addition. We need to do division and multiplication and subtraction, but not for our class. I just want you to show you what an addition problem looks like. So I'm going to start with a very, very simple one. And I can't stress this enough, that this is base 2. So if I use the number 1 plus 1, but we're in base 2. Okay. Now the idea is if you add those 2 together, we should get 2 if we were in regular base 10. But is there a 2 in regular base 10? Or base 2, I'm sorry. There isn't. The answer is either 0 or 1. So when 2 1s get added together, they don't equal 2. They equal a 0. So let me write this again. 1, 1. They equal a 0, and you carry a 1.